quite a long video and lesson by the time it's all finished. We are going to take a look at PyMOL, which is hopefully something that's going to allow you to really visualize what's going on with our amino acids in our primary structure folding eventually into that quaternary structure, which we will cover in the next proper lesson, because we've really got to go through some post-translational modification and a little bit of a recap of what's happening. However, I think it's probably going to be really good if I sandwich this one in between the two main lessons, so that you're going to be able to go from what we covered last time, which was the basics of all the bonding and the terminology for the bonding and how to view the bonding and the twisting and rotation of molecules around the bond axes, to actually seeing what's happening. And this is a really good program for this. It is a little old now. I think there are actually simpler ones that you can download, and they're a little bit more, they're a little bit easier to use, and they're a little bit less intense. They don't show you quite as much, but if you look on the App Store, you should find some protein modeling systems. There's no expectation that you guys can use this fully. I can't use it fully. The idea here is more to allow you to see what's going on and to give you an insight into how we can use computer programs to really help see what's going on, because we've got to remember these proteins are billions of times smaller than an individual cell, so it's important that we can exaggerate the size of these in our heads, but we've also got to remember that these work on a molecular scale, and they are really very small. So we'll start off here, and PyMOL is it's freely downloadable for 30 days, and you can also register to use it for educational purposes as a student or a teacher. So if you want to download it for the 30 days, that's fine. There's also other protein modeling software things that work on an iPad. A few of them are free, a few of them are paid for. I wouldn't honestly think it's necessary to go as far as paying for anything. If you like mucking about with it and looking at proteins, it is going to help you visualize what's going on, especially when we talk about proteins going forward. So this is the website, and you can download it for free for 30 days for educational use. You can register it if you want, so that you can use it throughout the year. Like I say, it's not required in any way, shape or form, but it might be really good for some of you who, I think, to be honest, for anyone, just visualizing what we're talking about. So what I'm going to do is show you the program, and this is what it looks like. Now, this screen bit here is where our protein's going to come up, but where we're going to get that protein. Now, we can just for the sake of argument, you can go to build, and let's get our simplest amino acid, and that is our simplest amino acid. Now, the red, if you go along to color, we've done this by element, and it's usually set as a standard that the hydrogen is in grey, the nitrogen's in blue, the oxygen's in red, and those carbons that you see there are in green. Now, there's lots of different ways we can actually change what this looks like. So if you click on L, you'll get some information about the labeling, and so you can label, you can see the labels for different elements. For example, if we click that, that's actually going to physically show me the names for these things. Now, it's important to understand that, especially if you don't have a background in chemistry, the more you label it to begin with, the easier it will be, but it's going to look clunkier. However, as you get better with things, you are going to be able to remove different things and look at it in a more straightforward manner. So I can show this as a, oh, so apparently already like that. Lines. Oh no, I can't. There we go. There's a little different way to look at it. Now, this is pretty interesting because what you're really looking at here is the inner lines that we've got. Those are really where the atoms are. However, the mesh really shows you where the electron cloud is. And when you're trying to imagine this, you can imagine it as if it's this semi-solid electron cloud. So even though the nucleus of the atoms are absolutely tiny, the electron cloud is a little bit larger, and the mesh there shows you how this takes up physical space essentially with those electrons, so that you're not going to be able to bash through that cage very easily with another molecule. You would probably have to use something like radiation to get through that cage, because that cage is a big negative charge, and you're going to have any other molecule that you've got, you're going to have negative charges there as well. So what I'll do is I'll chuck in another residue that we have seen before, and I think I'll go for, can I find it? Lysine, I think, is the basic one that we were talking about last time, and I will chuck that on there. That's got a positive charge, so this is our basic one that we had last time and we spoke about, and you can see that big long carbon chain that hopefully you saw in the Molly mod. Now that's going to be non-charged for the most part, and this bit up here is going to have a charge. So if we've got these two residues together, we've got, in fact, that could be quite a good, what I'm going to do is I'm going to delete all those objects, and I'm going to build you what we actually built with the Molly mods last time. And I think we had glutamic acid. That looks like it. Now, what you'll notice is this popped up slightly differently. I don't really like the way that it's popped up. So I'm going to try and alter it slightly. Well, I've got that mesh again. I might just go for the mesh. We can see it here. In fact, it's worth orientating this a little bit so that, in fact, I'll get rid of that. Can I hide that mesh? Hide the mesh. Let's hide the mesh for now. So I'm going to rotate this round. Right, that there is our amino group. And as you'll know, it's actually only got one hydrogen bonded to it at the moment. It's because the program is ready for it to be attached to another amino acid. So it's only got the one hydrogen. It's ready for another amino acid to come along. This bit here is our carboxyl functional group, and it is also ready for an attachment. It's missing the oxygen and the hydrogen off this end. Now this is another carboxyl functional group. This oxygen is negatively charged and the hydrogen has already left, creating that acid environment around. Now I want to see if I can show this slightly differently. Oh, okay. So a bit more like our Molly mod, much more realistic than our Molly mod, and like we just covered, that's really showing you what those electron clouds look like. So last time we had that glutamic acid, and I think I put alanine in, which looks like that. Yay, our little alanine. So we've got, I want to hide. So I want to go to hide, and I think I said spheres. So this bit here is the formation of our main chain, and these are our R groups. Oh, our R groups down here for the alanine. We'll see if that changes when we put in our lysine. So we'll put in our lysine. Ooh. Dear me. Right. Okay. Now I'm going to show my residues here. So EAK is my residues, and if I go to E is for glutamic acid, A is for alanine, and where were we? For lysine was K. So this is us, and I can select each one individually. However, at the moment, what I want to do is show all as a mesh. So this is what our mesh structure looks like. And if you remember when we were chatting last time, we said that this negative charge here might attract that positive charge there. So what I think I would like to do is auto sculpt. Which has not done a huge amount as far as I can see. It seems like it's probably reasonably simple enough that it just built it correctly anyway. Okay, so it's relatively simple, and that's what it looks like. Now we don't have what I'm going to show you later, and I might just pause and cut the video here and then come back, because I'd like to see if I can do something. So just to finish off really section 1, instead of using Molly mods, we have done exactly what we did in the last video with a computer modeling system, and we've got our 3 amino acids all linked together, and that's what we've got. And we can play about with it. We can show it as spheres and meshes and dots. We can also hide those things. So if I want to hide that mesh, oh, can I show? Oh, that's a shame. Okay, I would like to. Yes, I will come back to it once we're done later. But that is our amino acid string, so a very short polypeptide. And this negative charge here will be attracted to that positive charge there. And we might find that if I can figure out how to do the next little bit, that this alanine rotates round, but we'll have to wait and see. So as far as part 1 goes, if you want to try and pause the video here and do exactly what I've just done, so all you're doing is very simply using the residues that are available, and these are all your amino acids that you're going to find in the human body able to make proteins, and you can build a very short chain. It's worth noting that I don't think this has rotated yet into, or we haven't forced any conformational changes. That's actually what I'm gonna go and see if I can do to check that by adding in water molecules. So if you want, you can use the program and try and do this. I've changed the background color, so I did that through display, background, and white. I've kept an outline of this molecule in terms of the electron field, essentially. Now, when I had the mods, what you saw was there was a fair amount of rotation around those bonds, and I could connect directly these two together. Now, if you see where the electrons are, I couldn't, in reality, force these any closer than this. So this is the actual shape it would take up, and the positive charge here and the negative charge here has folded this molecule up, but they can't fold any closer together because we're now getting interaction between the aliphatic CH chains. So the electrons from here are kind of preventing this molecule from folding any more than it already is. So thankfully, the PyMOL system can actually prevent you from doing things that you could do with mods. So that's really as close as these things are actually going to get in reality. And you can see what these 3 amino acids kind of look like. It also means that hydrophobic section, this, if you can see this little bit here, our CH3, is actually forced down because there's no space here for that to pop up. Even though it is hydrophobic, it's not going to find space between these 2 R groups of the glutamic acid and the lysine. It's going to be forced down the way. So, just to keep it simple at the moment, this is really what you've got to be able to get into your head, that you've got these R groups that have charge. That charge is the function of those R groups, essentially. And because of their function, it will take up a very specific shape. So even with an extremely short polypeptide chain and just 2 points of formal charge, we've got an ionic bond kind of forming. It's not a classic ionic bond the way that I would imagine it, but it's certainly pulled these 2 parts of the molecule together like that. Right, once again, if you want to do this yourselves, you can get up to this point by just changing the background and the the system of showing you could do dots or the mesh surface, so that's a mesh surface in there like that. So this is probably the outer, well, technically the electrons can be anywhere in the universe, but we won't dive into that. This is probably showing the hard and fast surface and those electrons preventing these from getting any closer together than they are. Right, okay, what we're going to do next is take a look at a fully formed protein, and we are going to talk a little bit about how all the interactions, all the types of bonding help form those alpha helixes and those beta pleated sheets. What I am hopefully going to do, I'm on my second cup of coffee now, so I might be a little more enthusiastic than usual. What we're going to do is we're going to I'm going to show you how to get a protein up on PyMOL. We're going to have a little look at it, a little chat about it, and we are hopefully, for at least the first one, we're really going to take a look specifically at alpha helixes. So those are when we're talking about the secondary structure of a protein, what people are really trying to get at is really the main themes that we're seeing. So the alpha helixes, the beta pleated sheets, parallel and anti-parallel, and I'll show you the difference between the two using this system as well. This is what the main bits of the protein look like. These are the corner pieces, or the main characters, or however you want to describe it. These really show the proper foundational parts of the protein. There are going to be other bits of the protein that are very important that aren't alpha helixes and beta pleated sheets. However, when we're talking about the secondary structure, we're really talking about what does our primary structure mainly give rise to, and so we're gonna take a look at that. Now, I cannot build a protein on PyMOL. I wouldn't even have a clue where to begin. However, what I can do is I can go to the protein data bank or data bank. This is basically where people publish all of their proteins that they have created in PyMOL or other programs that they've used. And a lot of this comes from X-ray crystallography, which if you do chemistry, I'm not sure if it's in the advanced higher. I think it is a little bit in the advanced higher. Basically, you use X-rays and bounce those X-rays off molecules, and from that, in some manner or other, you can derive what that molecule looks like, and we can put that together with the primary sequence to create the three-dimensional vision of that protein that we see in the actual program itself. So that protein that will pop up there is derived from the primary structure and X-ray crystallography, and probably some other means of figuring out what happens with that protein. So it's important to know basically that there's a lot of things that go into helping create what this protein looks like. It's not quite as simple as plug in the primary structure and the program will fold it however seems reasonable. There's a lot of other little pieces of information and work that goes into producing these. So we'll go into the home page just now, and as you can see, one of the main things that people are trying to work with or figure out is coronavirus, and you'll see that there's another bunch of proteins that people have put up, and they've got featured highlights. Gonna be honest, it's not something that I look at on a daily basis. However, if you do go into a field that is looking at proteins, modelling proteins, you probably keep track of what's going on a pretty regular basis, and it will become like reading the news. And over 3 to 10 years, if you did this every single day, you would probably become very, very well versed in proteomics. That is not the purpose of this stuff, however, and it's not the purpose of the advanced higher. The purpose of the course at this stage is to give you the main foundations for how things work, and to give you a taste of what going down this path would look like. And this is hopefully just that. It's a little bit of a taste of what going down this path looks like. Now, I have pre-selected the protein that I want to take, and it is this one here. So if I click on it, I get a bunch of information. So this is part of the oxygen transport system. It's oxyhemoglobin. That is a scale. I don't like angstroms. Quite frankly, I don't use it, and I haven't used it very often. It doesn't mean much to me, unfortunately. That doesn't mean a lot to me. Now, this is pretty interesting here. We've got a residue count of 287. So the last time we looked at 3 residues. This time we're going to look at something that is a significantly larger, and this has 2 unique protein chains. Now, what they kind of mean by that is there's 2 separate polypeptides that have been rammed together in this one. This is not the quaternary structure, I don't think, for hemoglobin. This is only a part of that main structure. The structural weight is 32.4 kilodaltons. Now, this is another type of measurement I don't use a lot. It is related to GFM. So the GFM for this molecule, oh god, I think it would be 300 well, what we'll do is we will find out later. I'm not going to guess at that. I can't remember the conversion between Daltons and GFM at the moment, but we'll take a wee look at it anyway. Right, so there's a bunch of other information here which I'm not hyper interested in, and I'm not very interested in this. I really just want to do some of the very basic stuff, and this is my code for this particular polypeptide and part of the hemoglobin protein. So I will hit this, and I'm going to fetch, and I think it was 1HHO. So all I did there was type in fetch and 1HHO. You can also do it this way, where you can get from here. So there's a few different ways to do it, but it's easy enough to just hit fetch. Right, this is us. We've got our first at least part of a protein, and we are going to want to have a little look at it and a little play about with it. There's something very interesting there that to me looks maybe like our iron ligand with our diatomic oxygen attached. What the hell that is, I don't know. Not sure. That thing floating in the air, not sure what that is. We might have to do a little bit of further reading. But we've got Certainly to me, that looks like our oxyhemoglobin complex, and we've got another one over here. Right, those are just surrounded by these helixes, and these are our alpha helixes. And what I want you to imagine is that all those bonds that we spoke about in the first proper lesson and the preamble lesson in the chemistry, all those bonds help form these alpha helixes. So when you, if I'd like you to imagine in fact, what we'll do is we will show the residues. So I want to, where are you? Right, that residue is there, and it's T. And if I go to, where's my little, oh no, oh, don't tell me I got rid of it. Oh no. Right, hold on, give me a sec. As you will have figured out by that, I don't know this off by heart. If you work with this all the time, chances are you're going to figure out and you're going to know off by heart what all the letters stand for. It's basically just 5 times harder than the DNA stuff, and it's not required that you know this. The thing that would happen over time if you were to study this is you would learn this off by heart, but there's no need to do that just now. Oh, right. One that I'm not particularly familiar with. Theronine, I think. Right, let's take a wee quick. I want to actually not look at that. This is how I'm recording it, by the way. This is OBS, so you can record your home screen like that, and that's how I'm making videos. And I want to go into teaching from home. Not that it's going to pop up. Aha, here we go. Right, so you guys are advanced hires. We're going to be taking a look at this later, but we're not going to take a look at it for now. So, I want my 20 common amino acids. Where are we? Ooh, interesting one. Right, this is what we are looking at here. So I've selected one amino acid out of all of them. It's at the start of that big alpha helix chain, and this is it. So what we're going to do is we're going to try and see what all, well, not look at all, but see if there's any themes to this alpha helix. Right. Okay. So I'm going to click Control. I'm going to click that. Where's you? You're there. Right. Okay, I'm going to see. Where's that going? Is that going the right way for me? Yes, I think. Okay, fantastic. Right. Now, what I'm doing here is I am just highlighting all the amino acids in this particular alpha helix. So this alpha helix is sitting out here. There's a tunnel right down the middle, and we've got all of these different amino acids in here that are all interacting to cause that. Now, I'm going to go over here and click all. I'm going to rename this section, and I'm going to call this alpha helix 1. Okay, and then hit enter. Right. So, alpha helix 1 is this little stream of amino acids here, and I'm going to colour it a slightly different colour. I'm going to go for brick red. Okay, don't know if I can get much closer to... Oh, this is a pretty good one. We can get quite close. Right, so this is our alpha helix that we have highlighted here. In fact, technically speaking, this bit is a little terminal bit of the alpha helix. That might be the terminal. Is that the terminal chain? Yes, it is. So there's a wee break there, which suggests very strongly that this is our first polypeptide chain that we've got running to here. Now that polypeptide chain is then linked non-covalently to another polypeptide chain, and both of these polypeptide chains together interacting through ionic bonds, van der Waals attractions, and probably some disulfide bridges are linked together, and the singular polypeptides being added together will create our quaternary structure eventually, and we'll do a whole lesson on that, because that is, it's a little bit tricky to talk about, but I will try my best to get that information across as well as I can. So, alright. I want to see. Oh, no. Oh, God. Right. Well, apparently I don't know quite how to hide the rest of the structure and keep this bit, but we can definitely see that. Actually, that's making it look a little bit horrendous. I don't want that to be looking that horrendous. Right. So what I'm going to try and show is maybe the mesh, and that's going to show me the mesh for all of it, which is not what I wanted. I just wanted the mesh for that alpha helix. Ooh, here we go. Right. Now, what I've done there is I've wanted it to be labelled with the actual name of the residue that we've got. So, as you can see, we've got there's similar ones popping up over and over again. So I think that's valine. Ooh, come out. Right, Val is what we're looking for. Ah, valine, good, okay. So we've got a bunch of these. So what you've got to think to yourself is, right, what would this particular one be bringing to the table? Well, what it's bringing is just a hydrocarbon chain, and you know that that's not going to have much charge. It's going to be fairly hydrophobic. It's got no real polarity, so that's the task of that amino acid. So if we take a look at all those valines that we can see popping up there, and if I rotate it round, you can really see them there. I hope you guys can see them anyway. So they're all performing that function, and you'll probably find that the positions of those valines are really crucial in building up the alpha helix that we have there. Now, what I'd like to do is select another alpha helix and colour a different colour, and then we will see if we can see any of these similar amino acids. So we don't have all the amino acids in this chain here. We've got valine, we've got alanine, serine, leucine, and that one, threonine, I believe it was. Okay, that's not what I wanted to do. Yes, we've got quite a few of this one as well. Now, it's very worth noting that because we've got a hydroxyl group here, an OH, that's going to be able to form hydrogen bonds. So this bit here, very polar. So that's really what all those are going to be doing there. Right. Okay. Let's pick another one. I think what I'm going to do is hide the labels from that and hide the... I think that's just because, I think it's because I've got it selected. Yes, right. Now that I've coloured it, hopefully I can just deselect it and that puts it back. Right, very nice. Now we've covered one alpha helix there. Now I'm going to pick another one here. I click that right. So we got the end of it. I think we got the end of it. I'm going to pull out a little bit from this. And, ooh, no. Look, that one goes right the way here. Right, and I want to, yeah, deselect that. Right. Okay, now this alpha helix is really interesting because we've got a really weird kink in the alpha helix. It's all, PyMOL's considering this pretty much all an alpha helix. This bit's really contorted, so it might be interesting to see what that looks like. Now, oh dear, oh no, I just lost it. That was good. Right, now, I could either be going this way or this way. But quite frank with you, I've got no idea which direction we're moving in. So what I'm going to do is hit Control on my keyboard and then click the other end of it down here, which is not working. That's really aggravating. So all I want to do is see which direction I go. If I click that, and that is the right way to go. So I'm going to take this, oh that's far too big a chunk. Less of a chunk. Much less of a chunk. Okay, so that's me selected all of this kind of weird twisted round alpha helix. So what I want to do now is rename this section, and I'm going to call this alpha helix 2. Right, now our alpha helix 2, I want to colour this. Ooh, what will we go for? TV orange. Oh, delightful TV orange. Right. Okay, so now I have coloured in both of those different colours. Now, if you remember, for this one, we had lots of alanines and valines and threonines. Let's label and see if we can label the residues by name again. Ooh, right. Once again, really useful for me because I can say it so easily. The threonine is popping up again. The alanine's popping up again. Now, this weird bit here, we've got glycine. And that residue, that amino acid, is probably causing that weird kink in the alpha helix. So that glycine is interacting with both the other parts of this protein, and most importantly, what I'm going to show you next is the water molecules. So this is our oxygen. Now I'll change that oxygen and that oxygen, and I'm going to make them a nice marine blue. No, go back, edit, undo. No, it's not undoing it. Oh dear. Okay, what I want to do, I'll deselect these. We'll go back to this guy, and we will colour. What did we go for? TV orange. There we go. Right, now our oxygens are blue, and we can see that this hemoglobin can carry those oxygens like that. And we'll go back. What I want to do is actually deselect this entire thing. So there we go. I deselected that, and I'd like to hide the labels if I can. Oh dear. Okay, I'm gonna go back here. I want to hide the labels because it's a bit ugly. And then I just want to deselect that again. Right, okay, so we've got our very, very standard alpha helix in red there, and our weird kinked, probably because it's got those glycine amino acids that we didn't see in this alpha helix over here. It won't just be the fact that it's glycine, it'll be the way in which all of that interacts together. Now, what I wanted to do was show you the water molecules. Now, if I have taught you before, you have probably heard me mention a few times that you are a watery bag of protein. And that water is really important because the water in itself, that water is going to interact with our protein, and it's going to form bonds. The protein itself wouldn't look the same if it was completely dry. So these water molecules, and I wonder if I can colour them. We'll go for, that'll do. Fine. Now, what you've got to remember is that the water that you are about 67% made up of will interact with that protein, helping form its shape. So you can see that this part of a hemoglobin molecule is just surrounded and interspersed with water molecules, and that helps all of this form the shape that it's in. Those water molecules are able to form hydrogen bonds, and that will cause conformation changes in the protein. It's why you need to keep yourself hydrated, because you need that water to be interacting with your proteins. So this really overall highlights the use of these alpha helixes to create a very specific shape that allows this protein to do its function. Now, the heme group that we've got has our oxygen attached because it's oxyhemoglobin, and that will be able to make its way round the body and be delivered to different organs so that we can do some aerobic respiration, and it will go back to the lungs and pick up more oxygen and go round and round and round and round again. So the secondary structure are those alpha helixes, And the only thing at advanced higher that you need to be able to say and state outright is that the types of bonding, and then list the types of bonding. So ionic, disulfide bridges, the van der Waals forces, all contribute to that formation of that alpha helix there. And the two alpha helixes that I've highlighted, one's got that little weird bit in it. Maybe it's the presence of that glycine that changes the shape there. And that shape change is going to be important for the functioning of this protein when it's working. If you wanted to find out what impact that little bit had, what you could do is you could mutate your DNA strand so you alter the amino acid sequences so the residues here are different, and that may not take up the same shape as it does, and you could see if the protein is more or less effective at its job. Right, so those are our alpha helixes. I will be giving you a proper note in the next lesson about these. However, I think it was nice for us to be able to show them like this. The next little bit that we're going to look at is our beta-pleated sheets. So we're going to take a look at a protein with some beta-pleated sheets. So admittedly, this is now stretching on for nearly an hour. I really enjoy this stuff, but I appreciate time has been getting away from me somewhat. Now, what we've covered is the little alpha helixes that we've got here, and we spoke about why the interactions between the R groups might form these alpha helixes, or at the very least these are the shapes that those interactions form. The other main thing that we need to talk about is beta-pleated sheets. Now, I will give you a proper note on this, but for the time being, what I want to do is I want to select this one and I want to show our strands again. And here we are starting there, and these, because the arrows are pointing in opposite directions, these are anti-parallel beta-pleated sheets. And what I want to do is see if, right, that's going the wrong way. Is this going the right way? Ooh, that looks like it's, yes, okay. Right, okay, so once again I am gonna just rename this section anti-beta sheet, and I am gonna color this, and I like that fire brick red. Ooh, right, that's not very good. Now, well, it highlights a very important little function. Okay. Right. For the alpha helix, I think you will have noticed that it was really easy for me to pick out an alpha helix from start to finish. The beta-pleated sheet is not quite so straightforward. Now, I've managed to pick out two of them, which is quite nice. And what I might do is take a look at, so that's this one, and this one is, where are you? Here we go. What I want to do is just pick on all of these ones here. I want to deselect that one. No, no, deselect, nope, nope, ah, oh dear. Right, I'll come around here and we'll try and deselect you. And I'm just selecting more stuff, that's not very useful. And I'm not quite sure where these ones are. Oh wow. Right. So I'm not even sure where those residues are. It doesn't matter. What I'm gonna do is I'm gonna color my selected ones. Let's go for that TV orange again. Okay. Right. Now, that was so difficult to figure out where things are, simply because, as you can see, the beta pleated sheets are not necessarily made of a contiguous line of amino acids. They can be formed from different areas quite far apart in the polypeptide primary structure. So these two ones in green here and these two ones in orange, they all form part of a beta pleated sheet, but they are not next to each other in terms of the order of amino acids. So it is important to appreciate that the beta pleated sheets are a little bit harder to understand. That motif is a little bit less obvious in terms of being able to simply look at something and say that it's going to form a beta pleated sheet. That's why a lot of the work that goes into this is quite detailed and quite tricky and quite interesting. But the main thing I'd like you to know for these beta pleated sheets is that they are lines of the polypeptide that pass each other, forming basically a flat surface. So I am gonna select these two again. Oh god, no. What have I done? Oh, I'm not having any luck with the beta pleated sheets at all. There. Aha. Right. And what I want to do is show you the surface here. And that surface is a nice flat surface for that section. Now, what I'm going to do is I am going to deselect this now that the surface is shown. Like that. Oh dear. Oh, I can drag it. That's quite nice. Right. Now, we're going that way. So that's forwards. Yes. Good. Okay, where was I? There. A little bit tricky. As much as this is tricky, it is fun, I would say. So, now I've got this other section. I'm just gonna label it something slightly different. So, this is the anti-beta sheet 2. Right. And what I want to do is I'm actually going to colour this. I'm going to make it really obvious and make it teal colour. And what I want to do is show the surface of that. Now, what I'm going to do is show you the surface of the entire area. But if you note at the moment that the surface for these beta pleated sheets It's not perfectly flat. It isn't perfectly flat, but it is relatively flat. And what I want to do with all is show the surface of all. Right, so over the whole surface, we've got those reds, as you remember, were alpha helixes, and that's all like undulating, and we've got this big cavern here, whereas our beta pleated sheet on the surface, and this is all one beta pleated sheet, but it's this section is contiguous with itself and this section is contiguous with itself. However, they are not part of the they are part of the primary structure, but they are not part of the same section of the primary structure. So this is one section of the primary structure, and this is another section of the primary structure quite far away. Like you can see here, this is the primary structure here, and these are our residues. Now, between those two bits that are side by side, we've got all of these other residues. And then we've got this. However, when we look at the structure of the protein, these are actually side by side, and they're helping form this anti-parallel beta pleated sheet, and that gives us that very specific surface that we have there. Now, that is probably not hyper important for the active site, but it will be important for the overall function of the enzyme. So even if it's part of something that's not really part of the active site, it still has an important role to function, and most proteins have secondary functions, or they need to be activated, upregulated or downregulated, which we will talk about later. And so these sections are important for those. So that is your beta pleated sheet. The parallel ones, the arrows would all be going in the same direction, and I will be giving you a proper note about that later. However, I will leave it there. This has taken a little bit longer than I had intended it to, so it'll be uploaded a little bit later than I wanted, but hopefully that was a fairly comprehensive view of how the primary structure of amino acids gives rise to the secondary structures of alpha helixes and beta pleated sheets, and we get the tertiary three-dimensional structure, which is basically what we're looking at now, by all of the interactions in terms of the bonding along with those water molecules. So I'd like you to remember, if you can, that this protein or polypeptide chain is only able to form the shape that it does in the presence of water. So if we show these as spheres, we've got all... Why red for water? Not good. Not good. I'll colour this blue. All those water molecules there help this protein form its shape. So it's the interaction between all of these bonds, the ionic bonds, the disulfide bridges, and the van der Waals attractions, which includes those hydrogen bonds, the dipole-to-dipole interactions, and the London dispersion forces, all help this primary structure form up as far as the tertiary structure. What we will do next time is we will take a look at quaternary structure, and then we will take a little look at a scientific article. I'm hoping this will be up soon, so stay tuned for that. When you get it, which will be when you get it. You don't know I'm saying this, so I'm probably going to cut this little section out. Probably leave it in, because I can't be bothered cutting it. Right. Okay, you guys have a good day. Hopefully that was useful, and don't get freaked out. You don't need to be able to use any of this. You just need to be able to chat about the the structure it takes up and explain why it might take up that structure with the fact that we've got this different bonding. You don't need to be specific about the bonding, you just need to be general. It takes up that shape because of these bonds that could form. You don't need to know what bonds will form an alpha helix. That is not something that I can do. It's not something that the advanced hire requires you to do. So hopefully you enjoyed it, and I will speak to you on Teams soon.